here's where you should be. So when you get to 17, all right? So here's the basic idea on 17. Calculate the stopping potential based on a work function of 2.3 and 419 waves. So mathematically, here's what's happening. So the whole idea is that the kinetic energy is going to be the difference between HF minus your work function. Okay? So you have to understand which each number is going to give you. So the work function is the bail to get Nathan out of jail. Okay? Right? That's the work function. And that's an electron volt. It could be in joules. You should be fluent and be able to work back and forth between the two of them. Now, what the wavelength is going to give you, and this is important, you have two different trons involved in this. You have electrons and you have photons, okay? And if you're having a salad while you're eating this, there might be croutons. Just saying. So, the wavelength determines what?
Energy of the photon.
The energy of the incoming photon.
Uh-huh.
Okay? So the 419 nanometers gives you the energy of the photon. Now, on the front, I tell you, okay, you want to use that 1,242 electron volt nanometers. So what this is E. Now, if you're hardcore, if you are absolute hardcore, pure physics, I'm into units kind of thing, you would take the 419 nanometers. Don't do this unless you're really, really into this. You take the 419 nanometers and you change that into meters, okay? Which would be 419 times 10 to the minus 9 meters. Then you would roll that into C equals lambda times frequency, okay? So then you would take the speed of light and you would divide that by that wavelength and get the frequency by itself. Then you would take that, and again, this is if you're absolute hardcore purist. Then you would multiply that by 6.626 times 10 to the negative 34th joule seconds, and then you would get the answer in joules, and then you would convert that into electron volts. And you can do it that way, and it works. It's a god-awful amount of work, it's a god-awful amount of calculations.
I would never do that.
I'm just saying it's an option.
Why would we want to torture ourselves, Barry?
So, or you can sit there and go, wow, because of the fact that, but this is where it comes from. So, since C equals lambda times frequency, C over lambda equals frequency, so you can rewrite that as HC over lambda equals energy. So if you take Planck's constant in electron volts, multiply it by the speed of light, this is where you get that 1242 electron volt nanometers. Now all you have to do is take that number and divide that by the 419 nanometers, and then you just get electron volts.
Right.
Okay? Now, if this is going to work, no pun intended, what is this value have to be bigger than?
The work function.
The work function.
Because then nothing happens.
Because if it's not bigger than the work function, then
Stuck in jail.
yeah, I'm not going to, even if I'm at 2.3299, I'm not getting Nathan out of jail. No matter how much I knock on the judge's door, if I don't have that amount of money, I'm not getting Nathan out. So here's the bigger idea, is that this is what you bring. You have to give some of that to the work function mafia. What you have left over is what you can go with. So what this is telling you, this is how much the electric field you would have to adjust to, even though they're free, this is what you're going to set up to make it stop. And this is the reason why. From a physical apparatus standpoint, it's very easy to turn a knob and fine-tune an electric field, okay, to adjust your voltage. And if you want to go from positive to negative, you take the leads and you cross them over. Oh, I want this plate to be positive, I want that plate to be negative. Physically, undo the alligator clamps and put them on opposite sides. Okay? That's all you have to do. That's it. You want more voltage, take the knob, turn the knob. Boom, there you go. Okay? So, that's why that's something that was easily measured. Like you would physically see a current. Oh, let's crank up the voltage until it stops. That then became your stopping voltage to stop the electrons, because that's easy to manipulate. To sit there and physically fine-tune a wavelength to 419 nanometers, tough to do. Okay, so then when you get down to number 18, okay, change the wavelength to 409, and you're going to keep the same voltage. So this is where we're in the section where you have to focus on what is happening, what are you holding constant, and what are you still changing. So what you should see when you do that is that some of the electrons still make it across, okay? Even at 409 in terms of that wavelength. Now, think this through. You went from a wavelength of 419 to a wavelength of 409. If you look at 17 and 18, wavelength got shorter. Wavelength got shorter. So did the energy of the incoming photon get bigger or smaller? Bigger. Bigger. Shorter wavelength, right?
Yeah. Because it's no jamming.
So so that's like me showing up and getting Nathan out of jail, as opposed to bringing $500. Now I'm bringing $700. Okay. So what you're going to see and what this program does is that not all of the electrons that are kicked out have the same energy. And realistically, this is wrong. Because if you look at this, like for example, sodium, anything that's complex, you have layers of electrons. Obviously, that light, as it comes in, can interact with any electron in that cloud. It doesn't just, oh, I'm only going to interact with the outer valence electron. But here's the problem. The inner ones, because they're much closer to the nucleus, are more tightly bound. Those are never going to get knocked out. So for those of you that are in AP chemistry, this is what we'll talk about tomorrow. In terms of like first ionization energy and how you know this. So first ionization energy is the amount of energy that you have to put in to kick out the most loosely held electron. This is how that relates to the photoelectric effect. So the electrons that are farthest away have the weakest attractive force because you're dividing by the biggest distance. So those that are on the outside, those have the smallest work function. So you talk about a work function for an element, but in reality, because you have this electron cloud, you might have some that still get kicked out, but they were a little bit closer, so they lost more of that energy. So this is why this program, as it goes across, not all of these have the same amount of energy, and that's realistically what happens. Because the Chihuahuas, some of them are closer, they still get kicked out, but it cost them more energy to get out because they were more tightly bound to the nucleus. Okay, so when you get to 19, set the voltage to 0, wavelength back to 419. Calculate the velocity of the electron. So at this point, you're going to be able to determine that velocity because you're going to know what the Kmax is. So if you look at this in terms of that Kmax, you know the number. You don't have to recalculate it. You already found it because you figured out what the stopping voltage was. What you do need to do is change the electron volts into joules and put that into 1/2 mv squared. So your answer to 19 should be something times 10 to the 5th. Okay? What?
For stopping potential, do they make it negative or no?
Technically, yes.
But
Because it's going to be a negative voltage. If you have it positive, don't worry about it, but technically it's
yeah, what's
negative.
that's what's 9/11?
No.
Now, when you get to 20, you're going to calculate the de Broglie wavelength. That should be a really small number.
Like times 10 to the negative 6. No? Times 10 to the negative 6.
Oh, you're off by 1,000.
If we're talking nanometers, is that a really bad GPU?
If you're in nanometers, it is a train wreck.
Like I
of a
ain't
GPU.
graduated.
Okay, if you're in nanometers, it is a train wreck of a GPU.
Wait, in meters?
In nanometers.
You
but
said,
in meters is it times 10 to the negative 6?
No.
No.
hey, Berg, you said 19 is like a really, really good GPA to the 5th?
Yeah.
Okay.
Okay. Now, let me explain how I want 21 to play out. Okay?
For 19?
The answer and your steps to 21 are going to be done on another sheet of paper. Listen to me. Everyone listen to me. Do not answer 21 in that space. There's not enough room.
We'll see. I'm just playing play stuff. I can't
Yes,
test
Sensei,
it.
I got you.
Okay. So what's going to happen here is that you're going to change this to the unknown metal. And we're going to try and figure out what that is. Okay? So, what you want to do, you want to be able to do this, and physically if you were doing this in lab, keep in mind, you cannot have an apparatus where you can fine-tune a wavelength and change it by 1 nanometer at a time. So here's the big idea. You're going to choose a wavelength where you get a current, okay? What I don't want you to do is just fine-tune that wavelength until you just get an electron going out, okay? Not the point of the story, because you could not physically do that in the lab, okay? So you're going to have this metal. You don't know what it is. You're going to set this at maybe, let's say, I'm going to go down here. I'm at 224, okay? Clearly, I have the photoelectric effect going on. I've got a current of 0.416, okay? So that gives me the energy of the incoming photon because I know the wavelength. Then, and this is what you would do in an actual lab setting, then you would use the battery to make it stop. So, to make it the current stop, are you going to go negative voltage or positive voltage? Negative. Okay, hey, I slide this over. I go to -7. Okay, clearly that makes it stop. Okay? But this I can kind of fine tune. So, -4.8.
They're moving.
0, got the current,
Oh.
-3.2, things are still being stopped. So what you're going to do is that you're going to use a combination of wavelength and voltage to find out the work function of this. So what you're going to do, you are going to write out a simple procedure. This doesn't have to be anything complex. You're going to say, hey, I'm going to set the wavelength to whatever value that you choose. Okay? Whatever that is. Then you're going to say, that's enough to create the photoelectric effect. I can get a current. Then you're going to set the voltage, whatever that needs to be, make it stop. And then from there, you're going to solve for the work function. Once you get the work function, then you're going to use that to identify the metal based upon the chart of work functions that you have. Okay? So what you're going to do not, in this procedure, just say, oh, I'm going to adjust the wavelength until it just starts to happen. It's not the point. You cannot do that in a lab setting. You're going to overload it, you're going to get a current, and then you're going to fine-tune the voltage to make it stop. Because that's what you can physically do in the lab, is you can turn that knob to adjust that voltage and that electric field. So from there, you're going to figure out the identity of it. So when you get done, here's kind of your guiding light. Could someone in this room take your procedure, replicate, plug in the numbers that you have, understand what they're doing, and achieve the same identity? That's your guiding light. Can you give your procedure, which is not going to be written on this lab?
Right.
Okay? And this doesn't have to be your doctoral thesis. This is not a 5-paragraph essay. You're going to say, hey, step 1, I'm going to set the wavelength to whatever. Step 2, I'm going to adjust the voltage to whatever value. Show me the calculations. Based upon the work functions, this is what I think I've got. So, right quick, okay, then when you get to 22, then you're going to return it back to sodium. Set the wavelength to 300 nanometers, set the voltage to negative 0.64. That has to be exact numbers. So when you get to 22, those numbers have to be exact. You should be able to type those numbers in. And then what you're going to see is that, hey, do all of those make it across? And that's kind of the cool visual aspect of that. Now, when you get to 23, this is where we're going to go back and look at electric fields and forces and accelerations, and we're going to go old school. Okay? So, when you get to 23, you're going to have the voltage. Okay? Then you're going to determine the force on an electron in an acceleration, assuming the distance across the place is exactly 1 meter. So, you're going to know the value of the electric field, and you know that it's an electron. You need to find a force. Then, you're going to go old school, and then you're going to find an acceleration. Your acceleration should be a really, really big number. Okay? Now, then when you get to 24, determine the velocity of electrons, assuming the work function is 2.304. So, on 24, let me kind of explain how I wrote 24. On 24, you're just going to say, hey, we're not going to have any voltage trying to impede this motion. We're just going to have it ejected with a certain amount of velocity, and that's what you're trying to find. So, but you got to use that specific work function of 2.304, and you have to use that wavelength of, yes. So that velocity isn't going to be the same velocity that you found before, because that was based upon a wavelength of 419. This is based upon a wavelength of 300.
It'd be the same process.
Same process. Yeah, same process. Now, what you need to ask yourself is that as it goes across, is it going to speed up or is it going to slow down? That's what you want to think through. So, that should get you through 28. So, I'm going to give you some time, kind of get through 28, and then we'll talk about the next part of it.
It's 20 to the negative 9 meters.
Huh?
For 20 to the negative 9 meters.
If you're in meters, yeah.